Is there migration of the audience? Which kind of hardness measurements did you perform?
Yes, maybe for this for that presentation we didn't mention it was the micro hardness picker by using Shimatsu. Maybe the information will be written in the paper.
Okay, thank you. So we can proceed with your next presentation that is about indentation behavior of additively manufactured stainless steel welded by tungsten, inert gas, and laser welding techniques.
Thank you for this introduction. In fact, this work was performed recently. Here we are investigating the thick welding and zero welding of additively manufactured 316 stainless steel. But what is the new for this work? Because already we have many studies on the welding of 316 stainless steel, but it was the orientation of the building itself. So the motivation for that work that additive manufacturing is already expanding during the past time. And for the 316 stainless steel, it's a good corrosion resistant steel with superior mechanical properties with a variety of industrial application. Therefore, we are investigating 316 stainless steel, and the same also for laser and TIG. They are widely used and suitable for AM, because we know that there are some dimension limitation for the additive manufacturing. We are using laser powder bed fusion. Therefore, for the assembly, it would be better to recommend which like technique to weld these base metals. So the objective of the study is to reveal the mechanical behavior of weld joints made of additively manufactured 316 steel with different welding orientation, welded by tau and laser welding. The materials, the 316 stainless steel consists of spherical particles with size ranging between 10 and 45 micrometer. We use this printing parameter for the base metals. And here is the chemical composition of the powder. Regarding the methodology, we performed 3 different printing orientation of the material, 90, 45, and 0 degrees. The welding methodology, it implies buttering. And here is the relationship between the building orientation and the welding. For example, here we defined that this joint is WJ90. It means that the welding direction was perpendicular to the printing, where here like 0 degree, WJ0, means that the welding direction was parallel to the printed layers, and here we have WJ45 due to the angle of 45 between welding line and the printing direction. The TIG welding technique, we used filler metal 316L to fill the 1 millimeter gap between the base metals, and pure argon was used as the shielding gas. Regarding the heat input, there was some little differences for the heat input. For the WJ90D, it was 0.38, here 0.36, and here is 0.34 kilojoule per millimeter. So we consider that this like not a big difference in the heat input. While for the laser welding, we were using this parameter for the welding processing. So the heat input for laser was about 0.5 kilojoule per millimeter. Here's a dimension of the tension test specimens. And now we go to the result and discussion of this study. Here we show that the EBSD of the base metal, this one was in the 0 degree, and here 45, and here's a 90 degree. We can see that when this line here is with dashed yellow line, this represents the printing layer boundary. And here we can find that the propagation or the formation of the grain boundaries will be parallel to the printing direction or perpendicular to the printed layer. While here in the 45 degree, we can see that the grain boundaries are extended with the angle 45. And here for the 0 degree, we can see here that the extension of the grain boundary in the same direction of the printing direction. And here, this is the IPF of the base metal. Maybe you can find that there is some preferred orientation for the 0 degree in 001 and 101, while in the 90 degree, there are some preferred orientation for 111 and 001. And for the 45, there's like median orientations between the 0 and 45. Here we compare the values of strength and ductility of the printed base metals with the literature. For this one, we find that the strengths of 0 and 45 were greater than the 90 degree. The specimen printed with 90 degree, and this is in agreement with the literature. While here in the elongation percent, we find that the 90 degree orientation will give the maximum elongation percentage or ductility. We start with laser welding results. Here we just remind you again that the WJ 90D, here is the welding direction perpendicular to the printed layer. For the WJ 0D, the welding direction is parallel to the printed layer. Here, the optical microstructure by laser microscope of the fusion zone, and here is like part of the base metal. So when we look here at the base metal, here maybe some, we will find that the cellular structure was nearly disappeared after the heat treatment. We performed like heat treatment at 1000 degrees Celsius for 60 minutes to relieve some thermal stresses. However, here after the process of laser welding, we will find that the base metal showed that cellular structure again. And when we make zoom about this area at the interface between fusion zone and base metal, we will find that the main grain is also extended here between the base metal and the fusion. The fusion zone of the laser welded joint, and the same also for 45 and 90. So it means that the laser welding has it is not having extreme effect on the orientation of the main grain boundaries in the base metal. And here the phase maps and IBF of the fusion zone. We find that for that angle 90, the fusion zone width is about 0.55. Then this width was decreased for the 90 degrees. In fact, the main reason here is that these grain boundaries are perpendicular to the welding pass, and then the heat flow or cooling rate here will be much slower than this one. And also you can see here that the size of the grains in the fusion zone are much greater than the size of the grains here in the 90 degree. And the main reason is that the orientation of the grain, which affected the cooling rate after welding. And here the CAM results. Also, you will find that the fusion zone has less misorientation than the base metal. It means that the 1000 degrees Celsius heat treatment was not sufficient for the stress relief after laser powder bed fusion. And for the penetration, for the hardness value, you can find that the penetration depth is increasing at this 90 degree, while here the difference between for the penetration depths between the fusion zone and base metal is nearly the same. Therefore, we can see that the hardness value of the fusion zone of this 90 degree WJ, the weld joint 90 degree is lower than the base metal. However, here in the W0D, the values are very close between the base metal and the fusion zone. And also the main reason here is related to the cooling rate after welding, which makes that grain size to be smaller than grain size in fusion zone of 90 degree. Regarding the tensile behavior, we find that the the vertical one here is the W0D, with the weld joint with parallel direction showed very similar stress strain curve as the base metal. However, here in the 90 and 45 degree, there was a reduction in the strength and ductility. And when we compare the fracture location of the weld joints, we will find that for the 0 and for 45, the fracture happened at the fusion zone. It means that there was some softening here in the fusion zone compared to the base metal. While in the 90 degree, the fracture happened outside the fusion zone, was in the base metal. And this is normal because there's very similar behavior for the stress strain curve. Regarding the fracture surface study, we found that most of the specimen also have this type of ductile fracture. This was laser welding. And here this is still some analysis of the mechanical behavior or the microstructure behavior during the tensile testing. We are still figuring out why that this fusion zone and the 0 degree give this amount of deformation more than that of 0 and 45 degrees. For the TIG welding processing, you can see that the microstructure of the fusion zone is totally different. Here, we cannot see that type of cellular structure. We already used filler metal, and this filler metal here shows like a duplex structure of austenite and delta ferrite. Furthermore, when we also compare the size of the fusion bore here, we find that in the 90 degree, the width of this fusion zone about 6 millimeter, while here in the 0 degree, it was about 4 millimeter. Furthermore, the size also of the grains here in the 90 degree, the size of the grains or the structure here was greater than that for the 0 degree. Means that there is agreement between the cooling rate in TIG and laser welding joints. And here we made some zoom on this structure at the fusion zone for this 90-degree, we find that the size here of the dendrite arms are greater than that for the 0-degree. And the main reason also is cooling rate. Yes, this is statistics for the size of these dendrite arms in the W90D and WJ0D. Also, the heat affected zone was having different widths for here in the 90-degree. Also, the heat affected zone size was greater than the counterparts in 45 and 0 degrees, mean that the cooling rate here was lower, and the material shows this greater heat affected zone widths. In order to confirm our notification or our work about this cooling rate, we studied the fusion zone by the EBSD and found that here this is the structure of the fusion zone in the 90-degree and 45 and 0. Firstly, we can see here that the grain size is relatively bigger in that 90-degree. In addition, there is a more important thing, which is the amount of delta Freight. So the amount of delta Freight is increased with increasing the cooling rate, meaning that this structure already have that higher cooling rate. And also we made confirmation about this delta Freight by using X-ray refraction. We found one peak here in the 90-degree, which was not found in 45 and 0 degree, in addition to using price scope to measure the volume fraction of the delta Freight. It was increasing with increasing the cooling rate. So therefore, the WJ0 will display volume fraction of delta Freight more than W90D and 45D. And here also the CAM displaying that when we increase the cooling rate, then we will have more misorientations. Okay, we still have time to see. And here is the values of the filtration tips representing that W90D was also having lower hardness values than that one for W0D. For the tensile behavior, also we got similar behavior for that W0D, and the fracture already also happened about outside the weld metal, while here in W90 and 40 it happens again also at the fusion zone. Also the fracture surface displayed this type of ductile features. However, in the W90 and W45, it displayed some voids in the fracture surface, and we attributed this presence of voids due to deficiency in the volume fraction of delta Freight. For more information, this was our recent publication about this work. And here's a conclusion of the work. I will not read all of it. And finally, I would like to acknowledge Business Finland for funding this work. Yeah, thank you.